Hello, today we will discuss Euler's Toitent function. In the previous video we have discussed Euler's theorem, and the difference between these two ones is that Euler's Toitent function is the number of integers which are coprime to n and which are less than n, and so this range must be from 1 to n, and the formula is given in such kind: n times 1 minus 1 over py, 1 minus 1 over p2 p second, and 1 minus 1 over pk. If we know that prime factorization of n equals p1 to the alpha 1 power, p2 to the alpha 2 power, and pk to the alpha k power. To show this one, let's imagine that at first n equals p1 to the alpha 1 power. So we can see that all of the integers which are not multiple of p must be coprime to n. So if we are given m and m is not divisible by p1, we can say that GCD of m and n must be 1. And for every other numbers m prime, if m prime is divisible by p1, GCD of m and n will not be 1. So we can see that all multiples of p1 which are less than n does not give us GCD 1, and all others will give us GCD 1. So total number of the numbers who are coprime to n must be p1 to the alpha 1 power minus numbers which are multiple of p1 to the alpha 1 power over p1. And if we take this p1 to the alpha 1 power out of brackets, we get that p1 to the alpha 1 power 1 minus 1 over p1. And if we look at this equals n, so we get the formula for only one number, then n equals one prime number into some power. It has no matter. In our case, it was alpha 1. Now let's prove that this function is multiplicative. And what does this mean? If we know that n's prime representation, that a equals p1 to the alpha 1, p2 to the alpha 2, up to pk to the alpha k, and we are given another number m who has different prime factors except p1. None of them equals p1 to pk, q1 to the beta 1 power, q2 to the beta 2 power, up to qk qt over beta t power. Then we will see that f of mn must be equal f of m times f of n. And to show this, we need to use the fact that imagine that n equals p1 to the alpha 1 and m equals q1 to the beta 1. So by using our formula, fm must be m times 1 minus q1, and f of n must be m times 1 minus p1. And what can we see about the number m times n? If we want to count the numbers which are not coprime to m times n, this number must be either multiple of p1 or multiple of q1. So number of integers which are multiple of p1 equals m times n over p1. And number of integers which are multiple of q1 equals m times n over q1. But we have counted numbers which are multiple of p1 and q1 at the same time twice. So we need to subtract this number, minus m times n minus p1 times q1. So this must be the total number of integers who are not coprime with m times n. So the total number of integers which are coprime to n, mn, must be given by the formula f of mn must be m times n minus this number minus m times n over p1 plus m times n over q1 minus m times n over p1 times q1. And if we expand this one, we get that mn times 1 minus 1 over p1, 1 minus q1, 1 over q1, and then plus 1 over p1 times q1. If we look at carefully this last equation, we will see that this must be equal mn times 1 minus p1, 1 over p1 times 1 minus 1 over q1. And this is what we wanted to show, because fm times fn also equals this number. So we have shown that if the number of integers, the number of prime factors are different from m and n, then we can see that this function is multiplicative, and it has no matter. Here we will have one prime factor or many one, because we can do the same operation for all of them, and we will see that such kind of permutation always works. And if we represent n as the number of n equals, in the beginning we are given that n equals p1 times alpha 1, p2 times alpha 2, so pk times alpha k. If we represent each number as unique, called n1, n2, nk, phi of n must be phi of n1 n minus 1 times, phi of n minus 2 times, up to phi of nk. And because we know that the phi of prime power equals this number over 1 minus this prime number, we can see that this must be n1 over 1 minus p1, 1 over p1, and 2 times 1 minus p2, up to nk times 1 minus 1 over pk. And clearly this is what we wanted to show, because the whole number n1 times n2 times nk equals n, so n times 1 minus 1 over p1 times 1 minus 1 over p2 up to 1 over pk. And now we have proved Euler's Toitent function formula for every positive integer n.